Okay, so again, we're continuing lecturing on here, kind of chapter 5, 6-ish. We really talked about last time. We got into really chemical reactions. So we talked about chemical equations and the importance of balancing chemical equations. Um, so remember, there are reactants, which are starting material. There are products, which are obviously the substances that are formed as a result of a chemical reaction. And remember, when we balance equations, first off, we always want to have the equations balanced. We always want to sort of use equations balance, which means, again, if you have an equation given to you and it doesn't appear to be balanced, you should probably take a moment or two to make sure that either A, it is balanced, or B, you need to balance it. And we do balance it by just changing the coefficients in the equation. So those are the numbers that come in front of the formula. We basically keep changing, obviously, those coefficients until we pretty much have hit the exact same elements or number of elements on each side of the arrow. Remember, we don't change anything other than coefficients, no subscripts or anything like that. It's important that when you are done balancing an equation, like we talked about, that basically two things are sort of met, I guess. First off, obviously, you do need to have the same number of elements on each side of the equation or the arrow. And secondly, all the coefficients need to be whole numbers, and they do need to be the simplest set of whole numbers. So we had a couple of examples there where we could use a fraction, for example, to balance an equation, which is perfectly fine to do. The difference is, as we talked about, that you do need to make sure that you get rid of the fraction before you get sort of the properly balanced equation. So again, even though we can use a fraction like we did last time to balance the equation, we cannot leave the fraction in the equation and have it sort of successfully balanced at that point. It would not be considered balanced. So it does have to be whole numbers. Again, to clear the fraction, you simply multiply the equation, all the coefficients by the denominator, and that will clear it out. Sometimes that happens, and it's sort of the only way to balance an equation is to a lot of times use a fraction. And the fraction is pretty simple. The top number is usually the number that you need. Bottom number should match the subscript of what you're putting it in front of. And usually where that happens is where we have sort of like a diatomic molecule, like oxygen, nitrogen, something like that, on one side of the arrow, and kind of that same element and multiple things on the other side. That's oftentimes where that does happen. We also talked about that, sometimes when you do have equations that involve polyatomic ions, sometimes it's a lot easier to sort of keep the polyatomic ions together as you're balancing the equation rather than go sort of element by element, and just sort of balance them as whole units. And that's sometimes a sort of a quicker sort of way of doing it. You definitely could go element by element like we did, make tables like we did. Um, but there's a lot more obviously distributed and stuff like that, especially with polyatomic ions, parentheses, uh, subscripts outside the parentheses, and all that kind of distribution. So we talked about balancing equations, and then I think where we sort of left off on was the idea of electrolytes. And electrolytes are basically substances that, when they dissolve in solution, they do result in basically ions being formed, and the result of ions being formed really helps them conduct electricity. So the presence of those positive, negative ions floating around in the solution helps sort of complete everything and allow electricity really to kind of flow. We talked about a few different types of electrolytes. We'll hit them again here individually in just a second, but again, there's strong electrolytes, which basically means 100% of it breaks apart into ions, and because of the presence of those ions, we end up with a lot of obviously free ions in the solution, and that really does allow it to conduct electricity really, really well. And a very common sort of example when we talk about electrolytes and sort of electricity is sort of the light bulb example. And if we were to look at the light bulb example, it would look again like this, where the presence of all those ions in that solution will allow electricity to be conducted really well. And again, the light bulb will sort of go off very brightly. There's also weak electrolytes, which are reversible type reactions. They mainly stay together, but they are able to produce a little bit of ions. So that production of the little bit of ions is enough to allow electricity to still be conducted. And again, if you kind of look at the light bulb example here, not as bright, obviously, as our strong electrolytes. So still able, though, to conduct electricity because there is still a few of those ions really floating around. And lastly, we sort of finished up talking a little bit about non-electrolytes. And these are substances that will basically dissolve in a solution, but they really don't produce any ions. And because there's really no ions that have been produced, as we can see, it really doesn't conduct electricity, and the light bulb basically stays off. Any questions on those things that we talked about last time? Okay, so we're going to talk about each of these individually here now. Again, just to reiterate our sort of electrolytes. Again, as we talked about last time, the strong electrolyte 100% dissociates, which is a fancy word way of saying breaks apart into ions. So 100%, again, breaks apart into solution, into those ions. So if you take some sodium chloride and you dissolved it basically in water, which is basically what this is representing, what you would have in that solution is really, you would have an aqueous solution of, kind of when you do this part of it, you basically will have an aqueous solution of sodium chloride. And because it's a strong electrolyte, what you would mainly have in solution is 100% these ions floating around. So again, like I drew, I think the other day, if we were to look at the solution, you would not see any of the sodium chloride units still together. 100% of them would be ions that are floating around. You have absolutely no sodium chloride units still together. And the result of that is obviously a lot of ions present, again, allowing electricity to be conducted really well. And that was our sort of very bright light bulb example. And that is different than what we see in a weak electrolyte. This is acetic acid, which is basically like vinegar. And the major component of vinegar there is acetic acid. And it's a weak acid, which means it will, when it is in sort of solution, it's a little bit different. What you mainly have in this situation is actually this acetic acid still together. So this is mainly what you got going on in that solution, is actually the whole thing still together. Again, this is acetic acid from acetate, ATE, acetic acid there for there. But it will still break apart, though, a little bit into these ions here. So we do get a little of these guys kind of produced. So in this solution, we are producing a little bit of ions, and that is still going to allow it to conduct electricity, but again, nowhere near what we would see in a sodium chloride solution. So again, if we sort of looked into the solution, we would mainly see the acetic acid really still together. Now, this would be sort of the predominant guy that's in that solution. But again, it would produce some H+, it would produce some acetate in the solution, and there would be a few of these sort of ions floating around. But really, the main situation in here is this guy's basically going to stay together. So how do we recognize, again, some of these differences here? There are certain ways or certain things you can look at, but one real way that you can look at sort of the difference between the two is when you look at the actual equation. And when we look at the actual equation, we talked a little bit about this, I think, last time. When we look at a strong electrolyte, typically, we see basically a one-way arrow. So like everything is definitely just dumping out over here to our product side. It's all basically one direction. And that's different than what we see happening here in a weak electrolyte. Again, in a weak electrolyte, we typically see arrows heading in both directions. Arrows heading in both directions, as I touched upon last time, is essentially a reversible reaction. So when we do see those, again, arrows kind of going one way and the other way, this implies a reversible reaction. Again, heading from basically reactants to products here. This is what is known as the forward direction. Going from products to reactants is what's known as the reverse direction. And I think we touched upon it last time. What essentially happens in sort of a reversible reaction like this is pretty much at the start, everybody's going towards the towards the product side. So everybody's heading, towards that product side. At some point, what will happen is you pretty much will build up enough products that some of the products will decide we're going back the other way. And at some point, what will happen is, as I talked about last time, and really the basis for, Chem 200B, is it will reach what is referred to as chemical equilibrium. And what it means is when it reaches chemical equilibrium, it doesn't mean that we end up with the same amount on both sides or anything like that. It is really talking about the rate. So it means that the rate of the forward reaction will equal the rate of the reverse reaction. And essentially it will lock everybody into place. And usually what happens in sort of a weak electrolyte situation is, it is mainly like this way, a little bit that way. So it is mainly kind of everybody hanging out on the reactant side, a little bit of those guys go in there. But again, it will eventually reach that chemical equilibrium. So we do see that reversible reaction happening. And that is definitely a very clear sign for us in this class that if you see sort of an equation that has those two arrows, that is a very big sign that you are dealing with a weak electrolyte. And what you should be thinking about when you sort of come across something that's a weak electrolyte like this is you should think about it in terms of when it's in solution. You should think of it as mainly being sort of together and not really breaking apart very much. But it will produce a little bit of ions, but it mainly is going to basically stay together. And again, our acetic acid here is an example of that. Any questions on that there? How do we know if, something is sort of a weak electrolyte, sort of a strong electron and stuff like that? For the most part, if you have anything that's sort of an ionic compound, so like metal and non-metal together, almost a pretty safe bet that that is going to be sort of a strong electrolyte. It's going to 100% break apart. If you have things that are not necessarily ionic compounds, but some covalent compounds, probably the most common sort of weak electrolytes that you'll come across are a lot of like acids or bases, for example. So for example, I think we'll see it here in a slide, but just in case, there are some like strong acids, for example, that are, and I think we might have talked about it, but we'll double check here. But there are some strong acids, and the list of sort of strong acids are like hydrochloric acid, nitric acid, hydrobromic acid, hydroiodic acid, perchloric acid, sulfuric acid. So these are a lot of really sort of strong acids, which would also be strong electrolytes. And, outside of that, if you come across something that's sort of an acid, so again, here we see something like acetic acid is sort of a weak acid. Hydrofluoric acid is a weak acid. Nitrous acid is a weak acid. Oops. HCN is a weak acid. So a lot of these sort of weak acids are, again, weak electrolytes. So a lot of times remembering kind of these 6 or so here that are strong acids is a good way going, okay, it's not one of those strong acids, it's probably a weak acid, it's going to be a weak electrolyte. For our purposes here, again, the arrows here will be a very good indication. By the way, bases as well kind of work the same way. Strong bases are also strong electrolytes. And a lot of strong bases actually have hydroxide in it, like sodium hydroxide, potassium hydroxide, and so forth. you know, calcium hydroxide, strontium hydroxide. So a lot of them have that OH in it, and that's definitely a strong base. A weak base, very common one, is something like ammonia, NH3, and that is also a weak electrolyte. So for our purposes, you know, that's sort of how you'll be able to probably identify things as sort of being a strong electrolyte or weak electrolyte. And again, anything that's sort of a traditional ionic compound, metal, non-metal together, usually is a fairly strong electrolyte. Any questions on that there? So when we do put sort of a strong electrolyte, for example, or just an electrolyte into a solution, what happens is it pretty much will start to dissolve. So if we take something like sodium chloride that's solid, and we do put it into water, kind of like that equation we were looking at there for this sort of physical change, we get these sort of aqueous solutions, right? And remember that when we talked about aqueous, again, there is a difference between this and something in its liquid state. Remember that something in the liquid state is sort of a pure liquid, like if we just had water by ourselves. Something that's aqueous would be if we took something like water that's a liquid and something like sodium chloride that's a solid. When we put these guys together, we get a sodium chloride solution that would get the aqueous symbol next to it. So an aqueous implies usually a solution. It implies that usually you take something and mix it together. And again, really a solution is two parts, as we'll talk about. The solution is the solute, which is the smaller part, and the solvent, which is the larger part. So in the example of the sodium chloride solution here, sodium chloride would be our solute, and our solvent would be water, and both of them together would make a sodium chloride solution, which would get the aqueous symbol. But, you know, how does it sort of disappear, for example, right? It doesn't really disappear, but it dissolves. But if you take some sodium chloride or salt and put it into water, it looks like it's gone, right? It just completely disappeared. And this is why sometimes people think it is a chemical change that's happening here, and it's really not. It's a physical change. But the way it's able to sort of disappear, if you will, is because basically water is a polar molecule, and this is the oxygen of water. These are the hydrogens of water. And basically the hydrogen part of water is more positive. The oxygen part of water is more negative. So when it breaks apart into these ions, and we kind of write aqueous next to it, what we're basically saying is these ions are surrounded by water. And this is the process known as hydration. And what happens is the negative side of water, which are the oxygens here, are attracted to the positive side of, or the positive ion, and basically surrounds them. Same thing happens for our negative ion or chloride here. When the chloride goes for a swim, the hydrogen part of water, which is more positive, is attracted to it and surrounds it as well. Basically, it does two things. It allows it to sort of dissolve and, again, disappear, quote unquote, there, and basically kind of dissolve. And it's really not sort of changing there because it is still there, basically. And we know it's still there in the sort of original form, and it hasn't really changed anything else because we could simply take a solution of sodium chloride, for example, which is basically just salt water. And if you decided to heat the sodium chloride solution, what would happen is you would essentially, as you start heating this solution, you would essentially start evaporating off all the waters. So you would eventually start evaporating off all these waters, and over here as well. All the waters would come off as steam. And at some point, what would happen is you'd be left with your positive sodium ion, for example, by itself. You would be left with your chloride ion by itself. And now these two things no longer have the water there. They could definitely come back and make a solid sodium chloride. So if you ever done an experiment or seen an experiment where they take salt water and they basically evaporate it off or heat it up, eventually all the water evaporates off and you're left with just the sodium chloride solid that's there. And basically, in its original form. It's kind of similar to, I'm trying to think here, it's kind of similar to what happened with, say, the silver chloride experiment. Some point in that experiment, you had silver chloride that was present. It was all sort of a solution, if you will. At some point, you kept heating it up until basically all of the liquid part was gone and you were left with just the solid at that point. You're basically heating up all the water part of it out of that solution and allowing those ions to come together. So this process of hydration is really important. It's what allows sort of a ionic compound for sure to interact really well with water. And this is why they're able to interact really well with water, because it's basically opposites attract there, positive, negative attraction coming together. And it does two things. It allows basically when you take some salt or something like that in water, it allows it to sort of dissolve and mix really well together. It also provides sort of a buffer, if you will, for the water. It prevents those ions from coming together because the attractive force between the two ions are very, very great, that if they are sort of near each other, they would want to come together. So the water sort of acts as a barrier there to prevent the positive ion, negative ion from coming back together. And that's why we see it happen when we evaporate off the water. For example, when we evaporate off the water, there's really no barrier there to keep those ions apart. And they're definitely just going to go perfect and come back together. And that's where you see sort of the reappearance of the solid occurring. And again, that is why this process here that we're talking about, making a solution, is considered a physical change because the sodium chloride is basically there in its original form. By heating it, you can get it back. And not to mention, if you really wanted to, as you're heating the solution, you could collect the steam and condense it back to liquid water and get the liquid water back. So you could then get basically both parts of your solution, the water part and the sodium chloride part, back together. And that's your classic definition of a physical change in this particular case, when we can basically get back our original substances in their original form by some type of physical means like heating. Any questions on that? And we did talk about this as well. Again, a non-electrolyte really is something that will still dissolve. So it will definitely still dissolve in solution. The difference, though, is even though it will sort of dissolve, it's really not sort of ionic, if you will. It will not produce any ions. And it's really that lack of any ions being produced that prevents it from really conducting electricity. So the purpose of sort of an electrolyte is you kind of need those ions there. The positive, negative ions floating around that solution helps it conduct electricity. And again, the lack of that in a non-electrolyte means that we definitely will not have any electricity being sort of conducted. Here's sort of what I was sort of writing on the other page there, but again, pretty much a lot of strong electrolytes are strong acids and strong bases and ionic compounds. So again, if you see any of these sort of strong acids, along with obviously the couple others that I put in there, like HBr, HI, these guys are definitely going to be strong electrolytes. You could assume that they'll 100% break apart. I'll put a little asterisk, like they have an asterisk here for sulfuric acid. Because it's a diprotic acid, the second guy is actually a weak acid. This part of it is actually a weak acid, but we'll consider it this a strong electrolyte. It is a strong acid, but this part of it is a little bit different because it does have two hydrogens. You'll talk about it when you go take 200B. Again, our strong bases do contain basically a hydroxide in them. So that's a very good way. And I think we might have talked about this before, but again, if you sort of look at the periodic table in terms of bases, you got like your sodium, your potassium, then you hang over there to calcium, strontium, barium, and stuff like that. So almost if you kind of go like this way there on the periodic table, and even magnesium sometimes is included in there. These guys with OH in it, like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, typically will generate strong bases. So you could kind of consider those guys as strong bases. Again, ionic compounds, which is our metals and non-metals, will definitely be usually a strong electrolyte. Here are just some of those kind of weak acids and bases, as we sort of talked about as well. Again, would be considered weak electrolytes. So here in this sort of column here, we would get 100% ions. Here in this column here, these guys is mainly what we would have, a little ions. And here are some examples of some non-electrolytes. Again, all these things are going to basically dissolve in water. They're going to be soluble in water, but they will not produce ions. Again, something like methanol, as we'll talk about, methanol looks like this. And because this OH part of methanol is really a polar bond, this guy's negative, this guy's positive, it interacts really well with water as well. Because again, positive and negative, so our oxygen and hydrogen can bond. So these guys will mix really well together. But again, these are all molecular compounds, covalent bonding happening here, no ions being produced in this process. And again, it's that no ions here, which means we have pretty much nobody conducting electricity. Any questions on the difference between strong electrolytes, weak electrolytes, and non-electrolytes? Okay, so this type of information is important because it helps us with certain types of reactions to try to determine, what is really sort of taking place in these reactions. And we're now going to start talking about some different types of reactions. And when we talk about some different types of reactions, there's different ways that we can sort of classify a reaction, sort of depending on what we're looking at. But what we're going to be talking about is really kind of two big types of reactions, or sort of big umbrellas. And underneath these umbrellas, in terms of types of reactions, we will find other types of reactions that are basically the same reaction, but are also sort of called something different. So there's sort of a main overall reaction that's sort of taking place. And then there's sort of underneath that individualized sort of reactions and classifications that we talk about. So the first sort of reaction we're going to talk about really is under the big umbrella was referred to as double displacement reactions. And what are double displacement reactions? So let's just talk about those first off. Double displacement reactions. Double displacement reactions have a general formula of AB plus CD. And first off, how we sort of recognize these guys as being double displacement reactions is what we see on the reactant side. And what we see on the reactant side are two ionic compounds. So we got a positive guy and a negative guy, and a positive guy and a negative guy. So we have basically two ionic compounds. And always what occurs in a double displacement reaction is basically the two positive guys basically decide to switch partners. So this guy and this guy will basically switch partners. And what they will make on the product side are two new ionic compounds. So A, which is positive, would then hook up with D, that's negative, and again make a new ionic compound on the product side. C, which is positive, will then hook up with B, that is negative, and make another new ionic compound. And that is your classic double displacement reaction. That is basically classically how you determine you're dealing with a double displacement reaction, is by looking at it and going, okay, I see two ionic compounds on the left. They're going to basically just switch partners. Couple of important things to realize when you are asked to sort of write the products on this side. And it does tie back to what we were talking about last week when we were talking about sort of balancing equations. If you remember, I said, first off, when you balance an equation, you want to make sure that you first off get the correct formulas and then balance the equation. And this is a common area here in sort of this chapter and stuff like this, where people do run into the problem of kind of what I call, I'm going to try to balance it and write the equations at the same time. And what I mean by that is very common in these sort of reactions, you're given just the reactant part, so just the guys on the left. And you have to sort of predict sort of what the formulas are on the right-hand side, and then you have to balance it. And very often people will end up with the wrong formulas on the right-hand side because they're trying to basically kind of balance it and write the formulas. So you want to keep in mind, as we talked about last time, that it's important to do it in that order, correct formulas, and then balance. And what I mean by that is if you had A and B and C and D here, you want to think about, this formula, for example. We'll just take like calcium chloride, for example. If I had calcium chloride, which was one of my reactants, and I could identify this as a positive negative guy. When I think about this guy, I want to think about this guy as just the basic units that make it up. What is the basic cation and anion that make it up? And it's these two guys. At this point, I'm not really concerned at all about sort of the two that's there. And let's just say, for example, it was together with sodium bromide here. This is also a positive negative guy. I would think of this guy as a sodium and a bromide. And what's important is when the calcium, for example, goes together here with the bromide, I would want to put these guys together properly. And that means that I would write the formula as CaBr2. Same thing here when I would do the sodium and the chloride, I would write the proper thing as NaCl. I would not write it NaCl2 because there's like a 2 here, so then I'm going to put a 2 here, and I would end up with the wrong formula. So again, sometimes people are overly concerned about the balancing aspect of it when they go to write the formula and they end up with the wrong formulas. So it's always the proper thing is just to go with the basic ions that make these guys up, put them together properly like you were doing nomenclature, and then at that point you could go, oh, I need a 2 here and like a 2 here, and now I'm balanced by putting the coefficients in. So it's a very common problem that people have. It's a very common mistake that people make is they try to do both things at once. Again, correct formulas, then balance, and you'll be fine. Don't try to do them both together. Now, when we talk about double displacement reactions, this is what I'm talking about in terms of sort of the big umbrella. So this is sort of the big umbrella of some different types of reactions, which are all at the heart of sort of double displacement reactions. They're basically, that is what's happening. They're double displacement reactions. But sometimes in a double displacement reaction, when we're doing these sort of switches here, when we're taking these ionic compounds and we're making these new products on the other side, we can end up with a solid that forms. And if we do end up with a solid that forms, that is what is referred to, as I scribbled over here, as was referred to as a precipitate. And a precipitate is basically a solid that comes from mixing really two solutions. So you basically got two solutions, and you got positive, negative ions in there, positive, negative ions there. You pour them together. At some point, a positive and negative ion will come together, and it will actually make a solid in that solution. And that is what is referred to as a precipitate. So for example, as we can see here, if we look at this reaction here, which is lead to nitrate plus some sodium iodide, these are both solutions here, as you can see by the aqueous symbols. But when we start adding the sodium iodide together, we do get a solid that forms, and it's this yellow solid that we see here. And that is our lead to iodide. And we also get some sodium nitrate that's formed. This is a balanced equation. We got the same numbers of everybody on each side. This type of equation is what is referred to as a molecular equation. And it basically tells us, what is there, what is reacting, and stuff like that. Again, this guy right here is our precipitate. So this type of reaction would also be classified as a precipitation reaction. So this reaction that we're looking at can be classified really two ways. It could be classified as a precipitation reaction because we did make a solid there on the product side. It is actually still a double displacement reaction overall, because when we look at lead to nitrate, that's a positive negative, that's a positive negative, and basically what happened is these two guys switched partners. The lead ended up with the iodine on the right hand side, the sodium ended up with the nitrate on the right hand side, and we have our double displacement that basically took place. So it is really a double displacement reaction. Most people would probably classify it as a precipitation reaction because a solid has been made. Any questions on that there? Now, does this equation really adequately describe sort of what is happening in this solution? And the answer is not necessarily. We could actually take this reaction and we could write another equation which really sort of shows us what is taking place in this reaction. And if we do that, we would look at these guys and use our understanding of electrolytes that we just talked about to basically sort of figure out what is taking place. So lead to nitrate is an ionic compound. As we saw, an ionic compound is typically a strong electrolyte, which means in solution, this guy right here is not going to stay together. It's actually going to break apart into its ions. And the ions that it would break apart into is lead with a 2+ charge, and it would break apart into 2 nitrates here. This 2 comes to the front, as you can see, and there's 2 nitrates basically in the middle there. The sodium iodide, also an ionic compound, means it's probably a strong electrolyte, which means in solution is going to 100% break apart into its ions. And there's a 2 in front of it, which means you basically have 2 of them. That means that would give you 2 sodium ions that are floating around and 2 iodide ions. Again, the 2 here gets sort of distributed to each of those ions in that case. So really what's happening on sort of when we take both of these solutions is we basically have all these ions floating around basically in there. Now on the product side, we get something that is made into a solid. In order for something to be a solid, it has to actually stay together. So in this case, we would not break apart this guy because it is a solid. And typically speaking, anything that is a solid, a liquid, or a gas, we pretty much do not break apart, are a weak electrolyte. All stay together when you're writing this type of equation here. So when we're writing this type of equation, if you have anything that's a solid, anything that's a liquid, anything that's a gas, anything that is a weak electrolyte, you basically would stay together. Anything that is basically aqueous and a strong electrolyte, you would break apart. And here we get again a metal sort of non-metal situation. This is going to 100% break apart, and in solution we would have some sodium ions floating around and some nitrate ions floating around there. And this equation that we just wrote really describes what is happening sort of in that test tube, if you will. When we look at this, this is what is known as the total ionic equation. Sometimes people call it the complete ionic equation, or sometimes people just straight up call it just the ionic equation, but one of those sort of things. And it's an equation that basically shows us what is really happening sort of in this test tube. in this test tube, we basically got some lead-2 ions floating around. We got some nitrate ions floating around. We got some sodium ions floating around. And we got some iodide floating around. But if all these ions were floating around, how are we producing sort of this yellow solid that's being formed? Well, it is actually being produced by looking at our total ionic equation, and we can actually write a third equation, which really tells us exactly what's happening here. And we could do that first off by looking at our total ionic equation. And when we look at our total ionic equation, if we look on both sides of the arrows, we should be able to find some ions that look exactly the same. So in this particular example, if we look on the left-hand side, I see 2 nitrates. On the right-hand side, I also see 2 nitrates. It looks exactly the same. Left-hand side, I see 2 sodiums. Right-hand side, I see 2 sodiums. Look exactly the same. These guys here that look exactly the same on both sides of the equation, these are what are referred to as spectator ions. And spectator ions, much like the name sort of implies, if you are a spectator, you are essentially just watching. You're not really involved in sort of what is being made. You're not really participating in what is being made. You're just there to sort of watch. You're really there in this case just to balance out the charges of everything that's going on there. And in this case, what we typically do with our spectator ions in our net ion, in our total ionic equation is we simply cross them out on both sides. So we cross these guys out on both sides. And that leaves us one last type of equation, which in this case leaves us the lead-2 ions plus the couple of iodide ions will come together to make PbI2, which is a solid. And this is what is referred to as the net ionic equation. And the net ionic equation basically tells you when you pour those guys together, sort of the lead-2 nitrate and the sodium iodide, what is really happening in this case is it is those lead ions that are going to find the iodide ions, and those guys are going to come together, and that is what is making all of that yellow solid here. Everybody else is still there. They're still floating around in the solution, but they're really not doing anything other than floating around in the solution, those spectator ions. But it is really when you put those two together is that lead ion plus the iodide ion that are coming together again to form that solid that is made. Any questions on that there? All right. So when we write these equations, these are three sort of important equations to be able to write our molecular equation, our total ionic equation, and our net ionic equation. We want to kind of follow those steps that we did. You want to basically write out the balanced equation. You want to make sure you got the proper formulas there. And then you want to basically find your spectator ions, cancel them out. And then what you're left with is the net ionic equation. So the question is, does the net ionic equation always, I think your question is, does it always end up with a solid precipitate? And the answer is yes, in this type of reaction, when we're talking about precipitation reactions, because that's basically what's being formed in this reaction is a precipitate. But the other answer is no. You can write a net ionic equation for a number of things that maybe don't have a solid involved. There's kind of three, as we'll talk about as we go through this chapter and about reactions. There's sort of three driving forces for chemical reactions, and three driving forces for chemical reactions are basically an electron transfer, the formation of a precipitate, which is what we're talking about here, and also the formation of water, for example. These are like three sort of driving forces for chemical reactions. And what that basically means is, these are basically kind of the three purposes for or reasons why chemical reactions occur. It's either to sort of transfer of electrons, form a precipitate like we're talking about here in a reaction here, or even form water. So for example, if we were to do one that involved an acid and base, which we'll see a little bit later on here in this chapter, if we were to do a reaction between acid and base, what we would end up with in our net ionic equation would actually be water, which is a liquid and no solid present. So yes, in the sense of you will always see a solid when it's involved in a precipitation reaction, but no in the sense of a net ionic equation should always have, say, a solid involved on the product side. Other questions on that? And as weird as it may sound, we'll even see it as well. You could even write a net ionic equation for sort of an electron transfer, which is really a redox reaction that takes place as well. So if we were to do this, we wanted to know write the net ionic equation for the reaction of silver nitrate with sodium chloride. So if we were to sort of take this reaction here and sort of put it together, we have everything in words. So the first thing we would want to do is really write the molecular equation. And it's basically saying the reaction of silver nitrate, so that would be AgNO3, and sodium chloride, which is NaCl. And first off, if you did this and you weren't really sure what type of reaction we're dealing with, you should recognize this as a positive negative guy, right? And this guy is a positive negative guy. So both of those things should basically point you to, oh, this is a double displacement reaction that's happening. So what does that mean? It means that I should basically take my two positive guys and switch them. Now, it's important when we go to the other side that, as we talked about, we think about these guys in their basic sort of ions. So the basic ion for silver nitrate is a silver ion and a nitrate ion, those two guys. The basis for this guy is a sodium ion and a chloride ion. So what we're going to do now is take this silver ion and put it together with a chloride ion. And now, since these are the basis of those two ions, that's a +1 and -1, that will give us the proper formula on the right-hand side, which, by the way, happens to be a solid. And we'll talk about how you know that it is a solid in just a bit. When we take our sodium together and put it with our nitrate, in this case, again, +1 and -1 gives us our proper formula here, which is sodium nitrate. And we're going to talk about how you know sort of which one's the solid, which one is not the solid here a little bit here in this chapter. This would give us our molecular equation. We would want to make sure that it is balanced. So we got one silver on both sides, we got one nitrate on both sides, one sodium on both sides, and one chloride on both sides. So this would represent our balanced molecular equation. Now, if we want to get to our net ionic equation, we would then break these guys up into our total ionic equation. So silver nitrate is a strong electrolyte, which means we would expect the silver ion to break apart and the nitrate ion to break apart. Sodium chloride, also a strong electrolyte, which means we expect the sodium ion to break apart and the chloride ion to break apart. As we were just talking about on the other page, this is a solid. So the only way it can be a solid is it has to stay together. So we would keep it together and not break it apart. And again, here our sodium nitrate is aqueous ionic solution, which means in solution, it really is going to be a strong electrolyte and break apart. And this would be our total ionic equation. When we have our total ionic equation, again, we want to look on both sides of the arrow, and we're looking for ions that look exactly the same. So here we see nitrate and nitrate looking exactly the same. We see sodium here and sodium looking exactly the same. So again, in this case, both of those guys here would be our spectator ions, right? And again, they're just watching, they're really not making anything. So we do cross them out on both sides. And if you do it correctly, and what I mean by doing it correctly is that you start with a balanced equation here and a balanced equation here, your spectator ions should always completely cancel out. So you should never have, like, on one side 2 sodiums and only 1 sodium on the other side. They should always be balanced and they should really completely cancel out always. If you find yourself in a situation where your spectator ions do not cancel out completely, my guess is you probably did not balance the equation correctly, or you have a wrong formula somewhere, but they definitely should cancel out always completely. And what we're left with is really what is taking place in this reaction when we mix those two solutions is the silver ion from the silver nitrate is going down and finding the chloride ion from the sodium chloride. And those two together have a pretty good attraction to one another. And they're going to come together and make a solid, that's a white solid in this case, which is silver chloride. And this would represent the net ionic equation. And really what is, really taking place in this reaction and what is happening in terms of this reaction taking place. Any questions on how to write those sort of equations there? Okay. So we'll finish up here just talking about and just showing the rules, and then we'll probably pick up with it tomorrow. But the question is how you determine the spectator ions. You determine the spectator ions in this step. So when you look at your total ionic equation here, when you look at your total ionic equation on the left-hand side of the arrow and on the right-hand side of the arrow, you should have ions that look exactly the same. So for example, on the left-hand side here, we have an NO3 minus ion. On the right-hand side, we have an NO3 minus ion by itself, looking exactly the same. Those guys would be spectator ions. We have a sodium ion, Na plus on the left and Na plus on the right. Those guys look exactly the same. So those guys would be our spectator ions, and then we would cancel them out. So that's what you want to look for, or how you find them is after you write your total ionic equation, left-hand side, right-hand side of the arrow, you should have ions that look exactly the same. Other questions on that? Okay, so as I was mentioning before, how do we sort of know, when we put these sort of guys together, would we expect a solid? Would we expect sort of non-solid to form? And that has a lot to do with basically solubility. And solubility, basically, if something is soluble in each other, they basically will mix. You won't get a solid, for example. If you mix two solutions together, you'll still have a solution, all liquid, no solid. If you mix something that's sort of insoluble with each other, you will get basically a solid that forms. So when we talk about solubility, it basically means the maximum amount of solute that you could dissolve in a given amount of solution at a particular temperature. So remember, a solution basically is, as we talked about there, made up of a solute and a solvent. Again, smaller part and larger part. So if you just think about, for example, if you take some sugar and you take a little bit of sugar and water and you dissolve it, it will dissolve. If you take like the big Costco sized thing of sugar and you dump it into a glass of water, at some point it won't dissolve anymore, right? And that's where we talk about solubility. There is sort of a limit to sort of how much you could get to dissolve in a particular solvent. So water, for example, can only take, for example, so much sugar before it's can't take anymore. So these are what are referred to as solubility rules, and solubility rules help us with ionic compounds determine whether or not we expect something to be soluble or something to be insoluble. if something is soluble, what that means in terms of when you write the formula, you basically give it an aqueous symbol. It basically gets that aqueous symbol next to it. If you look at the solubility rules and you find something that is insoluble, that guy gets basically the solid symbol there next to it. So these are some things that are typically soluble. So things that have lithium, sodium, potassium, ammonium. If you have any of those sort of ions in a formula, you don't have to look any further. There are no exceptions on the right, which means you would expect these guys to be aqueous. Also, if you have anything that has nitrate or acetate in it, there are no exceptions. If you have anything in the formula that has those guys, it's going to be soluble and should get the aqueous symbol. If you have anything that has chloride, bromide, or iodide in it, it should always be soluble. But there are some exceptions over here. And the exceptions are if any of those guys, chloride, bromide, or iodine, hook up with silver, mercury 1, or lead, then they are not going to be soluble. They're going to be the opposite, which means the opposite of soluble is insoluble. And these guys would get the solid symbol. Again, if silver is hooked up with chloride or bromide or iodide, then you would expect it to make a solid. Sulfate is soluble in everything except these guys. So again, if you have sulfate with silver, calcium, strontium, barium, or lead, it would not be soluble, but it would end up being insoluble and would make a solid at that point. So these are some rules that help us understand things that would typically are going to be soluble, and some things that can be insoluble. Any questions on that there? Here's also some more rules. These are guys that are typically insoluble, which means guys on the left here, if you see them in a formula, typically makes a solid. But there are some exceptions. The exceptions are lithium, sodium, potassium, and ammonium, which is what we saw in the previous one, everybody in group 1. If you have any of these guys, it would then become aqueous, and you would not expect a solid to form. Slightly soluble, most people kind of lean towards being insoluble. So sometimes you'll see this sort of slightly soluble, and most people lean towards that being insoluble. It does mean what it sounds like. It does have a degree of solubility, but most people will lean that towards being insoluble. Anything that has sulfide in it typically is a solid, unless it's hooked up with group 1 and ammonium or calcium, strontium, barium, then it would be aqueous. Carbonate and phosphates are typically insoluble or solids, unless it's hooked up with our group 1 and ammonia, which then make it aqueous. So this is how, when we take something like what we dealt with previously, which was silver nitrate plus our sodium chloride, made some silver chloride plus some sodium nitrate. We could use these solubility rules to assign our aqueous or solid next to it. So if we look at this first one, which is silver nitrate, and you may not be able to find silver on the left-hand side, but you can find nitrate. And if we look back, there's our nitrate. Nitrate is always soluble, and there are no exceptions, which means we can safely, as soon as we see that nitrate, put the aqueous symbol next to it. We could then go to this guy and go sodium. Okay, sodium is right here. It is always soluble. There are no exceptions. You really could stop at that point. You don't need to go any further, and you could go, I know this guy is going to be aqueous. But if you did want to look at the chloride is soluble in everything except for silver, mercury, or lead. And in this case, that is not silver, mercury, or lead. So it tells us it's still soluble. Now, if we look at this guy, silver chloride, again, may not be able to find silver, but we can find chloride. Chloride, as we just talked about, is soluble in everything except for silver, mercury, and lead. In this case, we are dealing with silver and chloride together, which means chloride is typically soluble, but because of the silver, it's opposite of that and becomes insoluble, and we would expect this to be the solid that formed. And lastly, here we could look at sodium. And again, sodium being group 1, there are no exceptions. And we could stop right there if we wanted to and put aqueous. We could also look at the nitrate as well, which is right here. Always soluble, no exceptions. Also tells us it's aqueous. So this is how we could use our solubility rules to help us determine, is something going to be aqueous? Are we going to produce a solid in this type of reaction, this double displacement reaction? Any questions on that there? Okay, so we will lay it up there.